And let's go through an example. Okay, so the first thing that we need to make sure, if we're doing any operations using phasors, the terms that we are doing operations on need to have the same frequency. If they have different frequencies, we cannot use the phasor representation because the phasor representation ignores the frequency information. It just assumes you're remembering what frequency the signal is at, and that information is not included in the phasor representation. So if these two signals were at different frequencies, I cannot add them using the phasor representation. Okay, so let's first convert V1 of t to the phasor form. So I need to fill in some number, and then we have the symbol for the angle, and then we fill in some number. So what's the first number? I think I heard 3. What is that? The magnitude of the sinusoid. Okay, so that's 3, and that has units of volts. And then in the angle symbol, what value goes there? 30 degrees. So the phase of the sinusoid, assuming it's a cosine. Okay, so let's make V2 into its phasor form. What numbers am I writing? 4. I am going to write negative 150 degrees for the angle, but let's not skip any steps. So we first need to start off with negative 90 degrees because this is a sinusoid. So also in my phasor form, I'm not writing down cosine or sine. It's all going to be reference to when the signal starts increasing. So since we assume that a cosine has a 0 phase angle, the sinusoid it's a cosine, except it's shifted by 90 degrees. So we just need to add a 90-degree shift to the phasor representation. And then it also has a phase of negative 60 degrees. This has units of volts. So this is for volts with an angle of negative 150 degrees. Any questions so far? Okay, now let's also write the same voltages, but just in the complex number format. Okay, so for V1, this value is R, the angle is theta. So if we write V1 in the complex number format, it's R cosine theta plus J R sine theta. That all has units of volts. Okay, so if we do all of the math here, plug in 3 for the R's, plug in 30 degrees for theta. This comes out to 2.6 plus 1.5 J, and this is units of volts. Okay, so that's the complex number representation of V1. Why don't you try to do the complex number representation of V2? So tell me what V2 is. Give me some number, some real number, and some imaginary number that represents 4 angle negative 150 degrees. Well, to 1 decimal place. Yes. Sorry, I don't think I put this on class question. Let me check. I don't think I put it on there. So don't bother looking at it right now. Just do the calculation. Okay, who got a value? Only 2 people? 3 people? 4 people? Okay. Okay, so the real part is negative 3.5, and the imaginary part is negative 2. I'm sure you can do this math, so just make sure you're getting the right values. Okay, now if we want to add these 2 voltages, so I want to do V1 plus V2. In order to do that, I need to keep this in this complex number representation, because what I'm going to do is I'm just going to add, sum the real parts of V1 and V2, and then I'm going to sum the imaginary parts of V1 and V2. Okay, so that is going to be 2.6 plus negative 3.5. These are both with units of volts. And the imaginary parts are 1.5 and negative 2. And all of these terms have units of volts. Okay, so this comes out to negative 0.9 minus J 0.5 volts. Okay, so this is V1 plus V2. Any questions on that? This is just complex number math, which you should already know. Okay, but our summation is still in the complex number format. So let's convert this back to a phasor representation. And for the phasor representation, to get the phasor representation from the complex number format, we want to get back, something of the form of a V1 here, where we have R, the angle sign, and theta. Okay, so that R is going to be the magnitude of the real part squared, the magnitude of the imaginary part squared, and take the square root of that. Okay, so we're going to, if we want to convert back to phasor form, we need to take 0.9 squared plus 0.5 squared and take the square root. This is negative 0.9 and negative 0.5, but once you square them, it doesn't matter. And the angle part of the phasor is going to be the arctangent of the imaginary part over the real part. So if you do this math, this comes out to 1.03 with a phase angle of 29.1 degrees. If I want to convert this back to the time domain, what is it going to look like? V1 of t plus V2 of t equals, what am I going to write? What's the magnitude of the sum of the sinusoids? 1.03. Okay, now we're putting frequency information back in. What's the frequency? Oops, I gotta put the sinusoid back. What's our sinusoid function? Is it a cosine or a sine? Okay, let's write it as a cosine. We need to put the frequency information back. What's the frequency of this sinusoid? That's everything in the cosine. I just want to know what the frequency is. What term here represents frequency? That's still too many terms. What term represents frequency? Omega. Okay, so this is a cosine with a frequency of omega. And what's the phase angle? .1. And this is units of volts. Okay, so if we just look at these two time domain representations of V1 and V2, it's hard to intuitively know that this is going to be the summation of the two. Even if we look at the phasor representation of V1 and V2, it's still kind of hard to intuitively know what the answer is going to be. But if we then take the phasor representation, go to the complex number form of the phasor representation, then we can add these signals up. And once we add them up, we can convert back to the phasor form. That's what we did here. And then from there, it's easy to go back to the time domain form. Yes?
How do we know that it's going to be like a cosine and not like a sine? Or, like, you know, for the time domain?
You mean right here, going from here to here?
Yeah, how do we know it's going to be cosine?
You can write sine here, but you have to keep in mind that, you know, when we, like we did here, if we put in a sine, we put in a negative 90 degrees. So you're going to have to change the phase angle. You're going to have to add 90 degrees to this to get the same thing if you put sine here. Any other questions on this? Okay, so this is just showing that we can add up, you know, it'd be very similar for subtraction. So we can add up sinusoids of the same frequency using our phasor representation. It's not that convenient because we have to convert to the complex number format first. But if you want to do multiplication or division, it does become a lot more convenient, because if we have the phasor representation of two signals, so now I'm not bothering to give you specific values. I just have R1 with a phase angle of theta 1 and R2 with a phase angle of theta 2. I don't have to convert to the complex number format. We can just use the phasor representation, and multiplying these two together would be multiplying the two amplitudes together and then summing the two phase angles. And that would give you the result of multiplying those two sinusoids. Dividing two sinusoids is similar. So just divide the two magnitudes and then take the difference between the two phase angles. So if you're doing multiplication or division, starting from the phasor representation, you don't have to convert to the complex number form. There's more operations that we can do besides addition and subtraction and multiplication and division. I'm not going to go over all of them. Your textbook has some more examples of that.
So are the only ones we're going to be responsible for on the test then addition, subtraction, multiplication, division?
No, not necessarily. We went over integration and integration and differentiation last week too. Okay, but so far, talking about phasors, this has been like a math class. So let's bring this back to engineering and apply this math. So the reason why we're doing this is because we're going to be working with sinusoidal signals that are time varying, because we're going from DC signals to AC signals. So let's look at what's going to happen if our phasor is going to be voltage or current, and we have, say, a resistor. Okay, so even if our voltage and current are AC, Ohm's law still applies. Okay, so V equals IR is still going to hold true for the resistor. The resistor value is something that is just going to be a constant, doesn't depend on frequency. But let's say I have a time varying current. It's a sinusoidal current. So this is going to be my sinusoidal current. Okay, so that means that I can represent my current I can represent my current as a phasor. I sub m is the current magnitude, by the way. And this is going to give me, by multiplying that current phasor by the resistance R, that will give me a phasor for the voltage across that resistor. Or if I just wanted to write everything in that phasor notation with the bar above it, it's still Ohm's law. We just have phasor representations for voltage and current. By the way, your book uses, for phasors, your book uses a bold capital letter. It's hard for me to write a bold capital letter, so I'm using the line above the variable to indicate a phasor. Okay, so the voltage and the current through a resistor are in phase. So what does that mean? If I was looking at, let's say this is my oscilloscope, and I'm measuring voltage across the resistor as a function of time, this curve on here would represent the voltage. Maybe that voltage with that looks like a sinusoid, and we wrote a cosine, so you have to have some phase in there. But whatever voltage I have, my current is going to be in phase. Okay, so the time at which I have the maximum voltage across my resistor, I will also have a maximum current. They're going to be at the same frequency. They don't necessarily need to have the same magnitude, but the maximums and minimums of the sinusoid that represents the current, so this dash curve is going to represent current. The maximums and minimums of the current are going to occur at the same time points as for the voltage. There's going to be no phase difference between the voltage and the current. They're going to have the same angle. Any questions on the resistor? Okay, this is not going to be the same as the case for inductors and capacitors. So let's look at inductors first. Okay, so let's say that we have current through the inductor. We'll use the same current that has some magnitude I sub m. It's a cosine with a frequency of omega and a phase of theta. Voltage across the inductor, we're not using Ohm's law anymore. What's the equation? V equals L di dt. So this is going to be negative omega times L times that. Oops, it's not cosine. times the current magnitude times sine omega t plus the phase angle. Or using some trigonomic identities, I can rewrite this to omega times L, put the cosine back, but we have to add some phase of 90 degrees. That's the trig identity. Okay, so that means that if I do the phasor representation of the voltage across the inductor, I have, if I convert that current to a phasor, I have the current magnitude, the phase angle is theta, and I added 90 degrees from that trig identity. I can get rid of that extra angle of 90 degrees because I can use that e to the j 90 degrees is going to be j, and from that means that my voltage phasor is going to be j omega L times my current phasor. So what this means is that, again, this is going to be the readout of your oscilloscope if you were to measure the voltage across the inductor. So this curve is voltage, and here is the time point for a maximum. Here's the time point for a zero crossing. Here's the time point for a minimum. Here's a time point for another zero crossing, and a time point for a maximum. The current through the inductor is going to lag the voltage by 90 degrees. So what that means is if we start from time equals 0, you can see that the voltage is increasing to a maximum. And then after a quarter period, it's going to start decreasing. At that point, if I were to plot the current on the same graph, my current would start increasing to a maximum value, and then it's going to start decreasing. So my voltage reached a maximum value at 90 degrees. My current reaches a maximum value at 180 degrees. My voltage went to 0 at 180 degrees. My current is going to go to 0 at 270 degrees. So it's always 90 degrees later than the voltage. That's why we're saying that the current is lagging the voltage by 90 degrees. So if I was to keep plotting the current graph, it would look something like this. So this is the current. Again, the magnitudes don't have to be the same. The important thing here is the positions of the maximums and minimums relative to the voltage. Okay, so when I have my my maximum voltage across the inductor, the current through it is 0. When I have no voltage across the inductor, that's when I have the most current going through it. So there's going to be a phase difference between voltage and current for an inductor. This is different from the resistor. The resistor, when I had the maximum voltage across it, that's when I had the maximum current through it. But it's not the case for the inductor. Any questions on this? Okay, capacitors are the same, except the relationship is exactly the opposite. So let me start from the graphical side first this time. The current is going to lead the voltage. In other words, if we start from time equals 0, the current is going to start increasing before the voltage does. So if I were to plot current, it's going to increase and reach a maximum. The maximum point is when the voltage across the capacitor is 0. So this is current, this is voltage. But just like the inductor, the maximum minimums are offset by 90 degrees. It's just 90 degrees in the opposite direction compared to the inductor. Okay, so that's a cycle of the current and voltage for the capacitor. So when my voltage is at a maximum, there's no current through the capacitor. When the current's at a maximum, there's no voltage across the capacitor. Mathematically, if we say we have some voltage, that doesn't need the phasor. So we have some voltage with some magnitude V sub m cosine omega t plus a phase of theta. The current through a capacitor is going to be C dV dt. And if we do all the calculus and some algebra, that means that the phasor representation of this current is going to be J omega C times the voltage phasor, or the voltage is going to be the current phasor divided by J omega C. And that means that the current is going to lead the voltage by 90 degrees. So it's still a 90-degree shift, it's just in the opposite direction. Any questions on this? Okay, so let's recap. These are our three elements. If we have a voltage across these elements and some current through them, there's going to be different relationships, which are written at the bottom of each diagram. So for the resistor, V equals IR. For the inductor, V is J omega L times I. And for the capacitor, V equals I over j omega c. So we can isolate or rearrange these terms to get the value of the element on one side. So for the resistor, it's V over I, which is another form of Ohm's law. For the inductor, actually let's just put V over I. If I put V over I, then I get j omega L. And for the capacitor, if I put V over I get 1 over j omega c. So because of this, all of these equations are now written so that these are the values that give the voltage to current ratio. We can define a new property, and that's going to be called impedance. It's going to have a variable of z. And if you just think about impedance as a substitute for resistance, we can have Ohm's law in the form of impedance. So instead of V equals IR, it's V equals IZ. Because this term represents Z in this equation. This term represents Z in this equation. This term represents Z in the third equation. And all of those, if I say Z is going to be any of those values depending upon the circuit element, that gives me Ohm's law using impedance, which is V equals IZ. Okay, so this impedance concept is going to allow us to do all of our circuit analysis that we did before. Before we looked, when we only had resistors in our circuits. So skip back to before you knew what a capacitor or an inductor was, and we were solving circuits that only had resistors. If we represent our inductors and capacitors in the circuit using an impedance, we can just do all of the same things all over again. We just have to remember how to calculate that impedance value. Okay, so the impedance of a resistor is R. The impedance of an inductor is j omega L, and the impedance of a capacitor is 1 over j omega c. This also tells us, this definition of impedance also will tell us what we already know. Because what happens for the inductor when we make the frequency 0? So we go to DC. What does the impedance become? That impedance also goes to 0. And when we were solving circuits with inductors, they're all DC circuits. If we leave the inductor there for longer than 5 time constants, we said it's like a wire, right? The resistance of it goes to 0. There's no voltage across it, just passes all the current. That's exactly what this definition of impedance is telling us. now what happened? But since we know this definition of impedance now we can look at the opposite case too. So what happens as we go to really, really high frequencies? What happens to the impedance of the inductor? Is it big or small? Big?
Big.
Small? Okay, how big?
Very big.
Infinity. It goes to infinity. You can be more specific. Don't just say big. I wrote the current is infinity. That means the quantity of the impedance should also go to infinity. Okay, so what does this mean? What's a high frequency signal? Obviously, we don't have signals that go to a frequency of infinity, but what would be high frequency?
I guess CPU clock speed.
So gigahertz, yeah, that's pretty high frequency. So instead of CPU clock speed, let's use, say, a Wi-Fi signal, right? If I wanted to block the signal being broadcast from a Wi-Fi router from other electronics in that router, what should I do? I couldn't hear you. Yes, you could do that. That's a little bit more complicated than the solution that would be based on what's on this page. I could put an inductor in series with the signal. Because if that signal has a high frequency, the inductor is going to have a lot of impedance. It's going to block most of that signal. So inductors are used, in a lot of filters, which you'll start learning next semester. Okay, let's look at the capacitor. So what happens as we make the signal go to DC? What does my capacitor impedance become? I heard big again, but I think I heard something else. So this becomes infinite if my denominator goes to 0. Okay, so that matches what we looked at. If we have a capacitor in a DC circuit, it becomes an open circuit if you leave it there for more than 5 time constants. But now what happens if we make the frequency high frequency? So frequency becomes infinite. Now the capacitance goes to 0. So capacitors are going to block DC, but they're going to be like a short circuit the higher in frequency you go. So the exact opposite case of an inductor. Any questions on impedance? We won't use it yet, I'm just defining it. But we're going to use this concept and look at all the circuit analysis tools that we've used so far, like Thevenin circuits and all of that, and we can use impedance to solve for example, for Thevenin resistances in circuits that have capacitors and inductors. Okay, so that impedance, because it's based on phasors, or we can represent the current and the voltage as phasors, that impedance can also be a phasor. It has real and imaginary parts. The real part is the resistance. And the imaginary part is something called the reactance. If that imaginary part is greater than 0, then that means you have something that's inductive. If it's less than 0, it's something that's capacitive. And all of those complex number math relationships still hold up for the impedance as well. The opposite of resistance is conductance. The opposite of impedance is admittance. So it's the reciprocal of the impedance. So admittance is Y, and that's the reciprocal of impedance. And this is going to also be a complex number. And it will have a real part that is conductance, and an imaginary part that's called susceptance. So what we will see is that Ohm's law still works with phasors and impedance. Kirchhoff's laws, KCL, KVL, they also work with phasors and impedance. If we can convert elements to their impedance equivalent, then we can do all the same things that we did with resistors. So, for example, doesn't matter what these elements are represented in the blocks. They could be resistors, capacitors, or inductors. As long as I am representing them as an impedance, if they're in series, I can add them up, just like resistors. If they're in parallel, the parallel combination will be the sum of all the reciprocal of the sum of all the reciprocals, just like a resistor. As long as, it doesn't matter what these elements are again, as long as I'm representing them by their impedance. Even if you want to do delta to y again, the equations all work as long as you use the impedances instead of the resistances. Okay, there's one example after this, but we don't have time to go over it. So I'll probably quickly go over that. Maybe. If we don't have time, then that's okay. But on Friday, I'm going to go over the practice exam. That's also your homework, which means if your homework is not in my hands by the time I start talking, I'm not going to count it because I'm going to be giving you the answers. So make sure you turn in your homework on time.